the simulator as we go along, and I'm also going to show you kind of the way in which the simulator can be programmed against. So let me try and find. Oh, threading is in Workspace. Right. So one thing you might want to do when you no, I need to come back to this afterwards. Let me come back to this afterwards. So here is the standard way that I open the simulator, and it's easier to see as I do it because there's all sorts of extras. So because this is the JIT, and I'm experimenting with different code generators. The first thing I've got is like this this thing that gives me a menu and asks me which of the subclasses of the JIT I've used, and I've got simple stack-based JIT, and then I have a stack-to-register mapping JIT, and then I've got a sister stack-to-register mapping JIT, which is doing stuff for some infrastructure for adaptive optimization, and then I've got something that does some checking, some tests as it goes along. So that's just some hack, which is going to change a class variable to use the specific kind of JIT that I want. But basically, to use the simulator, what you do is create yourself a simulator, and then send it any number of initialization messages. So there are messages to do with setting a breakpoint, and messages to do with asking it to print out bytecodes as it goes along, or etc. And you have to. I should do a blog post on what those ones are, and try and define the API. But basically, in the browser, you need to explore. And so, if you open a browser on Cog VM Simulator or the Stack Memory Simulator, there's and all sorts of stuff in debug support. That's not very good. Debugging traps. Okay, one good place to start is the utilities menu. So if I let this guy run for a little bit longer, oops, that didn't work. Oh, that's right. We've actually opened it, haven't we? Sorry. Oh, don't crash on me. Come on. Thank you. That's good. Here it is. That's right. So, yeah, as I was saying, one good way to start is by looking at this debug menu. And the debug menu, when you start off a simulator, once you've got your VM simulator, you ask it to open an image. And that will initialize all of the state. That will load an image and attempt to load an image, because of course it might create an error. And so what that does is populate various state. And so here is like the object memory that we're using, and in the object memory is oops, I shouldn't have done that. There we go. Let's not do that. You know, if I do self, I don't know. Hang on. Right. So here's what it considers the nil object. And so if I do self long at self nil object, I'll get the header of the nil object. It's actually accessing something in the object in this memory, this little endian bitmap of length, 50 megabytes, and that is holding all of the objects, and it's holding the stack zone, and it's holding the JITted memory, and the kind of memory map is. Let me show you where that gets set up. So if you have a look at open on extra memory, this method reads, opens the image, and then starts reading some basic values from the image. So there's the size of the image file header, and there's the size of the heap, and then there's the base address of the image, which is what was the address in memory of the first thing in the heap. Because when we load an image file, we have to accept that the addresses in there are the addresses in the memory of the system that saved the snapshot, and we have to fix up all of those addresses and adjust them to where we have it in memory right now. And then, this is the thing that finds the OOP of the special objects array, which is the root of the system from which we can restart. And then some unused stuff, and how big the window should be, etc., etc., etc. So this is the simulator method, but there's also a method which is basically the method in the real VM, read image from file, which does exactly the same thing, but this is the one that gets translated to C and used. And unfortunately, the way that the simulator was written is to have a slightly different entry point in the VM simulator that's almost exactly the same, but not quite. And so any hero who can figure out how to make this one exactly the same as the other one should go ahead, and we should only have the one method. But okay, so given that there's the various differences, here we are. Once we've read the header, allocating either the little endian bitmap or the bitmap, which is going to hold the whole heap, having calculated how much memory there is, and then. Oh yeah, that's right, the method cache is in there as well. In fact, we've got method cache and a trace log. And so what we're doing here is saying, okay, in the heap, I want however much memory for machine code, however much memory for the stack zone, however much memory for the method cache, however much memory for the trace of primitives that you can call, and then like a simulation thing only, which is when I'm simulating calls into the interpreter, I need to make calls from machine code as if they were calling into a C stack. So there needs to be a little fake C stack in the simulator. And then, so this method sets up the entire heap, and by reading that memory, you can get an idea for how things are laid out. So that's what happens here. So in the image header are things like how many pages to use for the stack zone, how much memory in 1K chunks to use for machine code, etc. And so the image header plus the size of the image is all that is needed for working out how to lay out the heap. So then there's once we've created a simulator, we can ask it to open as a morph, which is one really convenient way of playing with it. So when you open it as a morph, you get a window like this, where this is the display screen, and this is a transcript. And this is just informational, and it gives us the send count and the bytecode count as the simulator proceeds. And the simulator will count various things. So what I've done it here is open as morph, and then I've asked it to toggle the transcript, which means that it, instead of stuff coming out here, it comes out here on the main transcript. Because while it's really useful to have a local transcript, you can't see anything because it's too small. So you end up using the proper transcript. And then when we actually want to start running, we just send it run. Well, there's a few run methods. So one is run with break count. And then there's another one, test. For example, there's something which will do tests of become, which will take an image that you've loaded and attempt to do some becomes on the image and do something. So that's an excellent place to. It's not an excellent place, but it is a place where you can put in tests if you want to play with the interpreters. Basically, you load an image and then you start, without running it, start playing around. And so one of the things that I do, which takes unfortunately an enormous amount of time, is load an image and go through all of the methods in the image and compile them to machine code, running some kind of consistency check. So I wanted to say, finally get on to saying what's a good place to look for the API. So where's my... There's a menu in this window, and that menu, here's toggle transcript, for example, at the top of it. This menu has a number of things that you might want to do. So at the top we've got sort of print the currently active frame, print the stack. So if I do this, oh come on, you can do that kind. Oh no, that's right. I have to actually step into run a little bit. Hang on. Let me get it a little bit further. Right, now we've loaded the initial context. Now I can print the call stack and see that so and guys, and Luke, I'm not saying don't whisper, because I'm quite happy for you to listen to whisper, but please don't be afraid to just say hey, right? And if something's confusing, just ask me, because it's like this is going to be dull otherwise. So let me show you where that is. So it's not at squeakvm.org. It is in here. So it's oh yes, it is squeakvm.org, but it's in the Cog branch, right?
I tried to start that with the Cog.
It won't work until you build the simulator. the box simulator. Right. So I'll go into that in a bit. Yeah, I can show you that. Actually, that's a good thing to show you soon. And I don't want to go there just yet. So in image are a VM Maker Squeak. No, yes, that's right. VM Maker Squeak image. Oh, and then it's not. That's right. Thank you. That's right. It's VM Maker. That's right. So yeah, VM Maker Squeak 4.1 image. So if I open that guy, this guy has. I should revert it actually, but never mind. This guy has a build workspace for pushing out the source, and here is a simulation workspace. You see that there's the title, and it's basically got a few examples, and here is basically exactly the same text, almost exactly the same text as I had in my workspace. I know it's not showing up, but it does. And then there's another workspace here for running the Smalltalk to C translator, so that you can punch out a single method. So that's a good place to start, and I try and keep that up to date. So basically, download the Cog sources, and open that image, and the simulator is set up there. But we'll come back to building the box plugin soon. So the basic facilities for inspecting execution, printing the call stack, printing a current frame, etc., printing the register set, inspecting the various major components of the VM, like the object memory and the interpreter and the JIT and the method zone, etc. But there's a lot of facilities in there, and unfortunately, none of it is well organized. So it's certainly not, beautifully laid out in terms of API, and it really does grow completely organically, right? You find some problem that you have to set a breakpoint for, or and so it grows in a very disorganized way. And all I can say is that if you want to use it, you're going to have to play and get your hands dirty and explore. It's never going to be perfect. The only time it's going to be really easy to use is when it's dead, right? When it's not evolving. So I know that's not a satisfactory answer, but just dig in and play. So the simulator, as we've seen, there's this huge byte array, this bitmap, which contains the entire heap in which we can play, and I want to show you some of the code generator. So the that's unreadably small, isn't it? That menu. Yeah. The main components of the VM are an object memory, which manages the heap of Smalltalk objects, an interpreter, and there are two main interpreters. There's the stack interpreter, which is just an interpreter with the context to stack mapping scheme, and then there's the co-interpreter, which overrides it to add interaction with the JIT and to be able to interpret and to run machine code at the same time. And then there's a JIT, And the JIT is a hierarchy. So there's an abstract JIT, which has got stuff to do with, well, I know I'm going to be producing machine code, and I need an assembler and stuff. And then there are some, see what I mean about these horrible instance variables? There's a simple stack-based JIT, which does no sophisticated code generation at all. All it does is each bytecode expands to a given sequence of machine code. And then there's a more sophisticated code generator which tries to do constant folding and mapping arguments to register, stack arguments to register arguments for certain sends. But the JIT itself is parameterized. So some of the really important variables in the JIT are, there's a method zone, which is the manager for machine code methods, which has all of the stuff to do with enumerating all of the methods and doing things like maintaining the list of open picks that we've already created when we want to rebind polymorphic send sites. What the free start is, where the free memory is, and managing the whole process of compacting the zone when we run out of space, and the list of methods that refer to young objects and stuff like that. But one of the most interesting decompositions in the JIT is this guy, object representation. So in the JIT, there's also an instance variable, object representation. And when I started writing the JIT, I knew that the current garbage collector would need to be replaced. So there is an abstract class called object representation, and it doesn't have any methods. It should have lots of subclass responsibilities. But and there is one subclass right now, which is the Cog object representation for Squeak v3. So the current image format is the v3 image format, and that's basically the one tag bit small integers and the compact classes and the 3 header words. And everywhere in the JIT where we access objects, the JIT actually defers to the object representation to generate that code. So the object representation is in some sense parameterized and pulled out into a different object in the JIT. So for example, the code that gets an inline cache tag in the prologue is actually something that is in a separate object. So if I was to re-implement the garbage collector and have a slimmer object representation, I should not have to change the JIT. I should be able to have it just in a Cog object representation for Eliot's object representation or whatever. So that's the plan, at least. So the VM is a bit more decomposed than a lot of other JITs I've seen the inside of. So
Can you use the same class for object memory?
you could, but that seems to be really
Compose object format from object memory to
yeah. I mean, I don't like that, because this class has to know an awful lot about JIT internals to know the assembler and stuff, and I don't see that belongs in object memory.
You can have 2 subclasses and one for JIT, another for C generation.
Oh yeah, I see what you mean. If you wanted to well, okay. I haven't done that. I haven't needed to. Anyway, don't make me think too much.
No, but really what is missing in this implementation is that we is some kind of description of object format and all operations.
Right. So.
Some single place where you can change it and change everywhere.
Right. And unfortunately, it's going to be spread over a few classes. So maybe when I implement the new garbage collector, I could introduce an abstract superclass which would just define the API and comment it. So that might be a good thing to do. So one of the things about keeping the interpreter and the JIT together is my experience with VisualWorks, where there is only a JIT, and the only way to execute Smalltalk is by a JIT, and that gives you great performance, but it also means that you waste a lot of time JITting huge methods. So in startup or when you run a class initializer, etc., if you run some method that is only run once, and typically class initializers are only run once, right, very infrequently, converting that to machine code and then running it is way slower than just interpreting the thing in the first place, right? So, you know, compiling is going to be tens to 50 times slower than doing a single interpretive pass, and it makes no sense. Further, if you imagine the kind of situation where you are executing some machine code and you get a send miss, so you have a method in your hand with a send site in it, and you are trying to rebind the send site and allocate a pick, and you run out of memory, and so you have to do a reclamation of the code space and choose some methods to throw away. This send site that you're holding on to that you want to bind to the pick may move, and the JIT is in the VisualWorks JIT is in this horrible place of being in some very, very tricky situations where to continue it has to cope with the fact that where it's suspended may move as it compacts the method zone to make room for new methods, and it's just very, very hairy and bug ridden, and you know, because reclamations happen, you know, at a maximum of say once every couple of seconds and things, to create just the right conditions to test this was really hard. And so it's much nicer both to save avoiding JITting for infrequently used methods, and for the JIT to be able to fall back on the interpreter and not have to deal with these tricky situations, to have both an interpreter and a JIT. So the VM keeps the interpreter and allows us to always fall back. So there's am I repeating myself from the first day? I don't know. So there's an interpreter and there's a JIT, and the interpreter is what starts running. So once you've loaded an image, the real start is here, and there's an opportunity to check that the image you've loaded is valid, and then the active process can be fetched from the special objects array, because the processor has the active process as an instance variable in it. So you know, it's like the fourth element of the special objects array is the processor association. So its value is processor, and its active process slot contains the active process, and from that you can get a context, and then we can start execution by creating a frame for that. So marrying the active context. So that's how an image is loaded and started up. And now we've got one frame, and if I print, where's my window? If I print the external head frame, here's the top frame, which is an activation of the snapshot method that wrote the image out. And so, you go up here, Smalltalk image, snapshot and quit, and here's save and quit, and that was invoked from the world menu, etc. And so now the system is ready to run. And indeed, run does enters the interpreter. So let's follow this guy in. And you remember I said ensure those multi-threaded overrides are up to date. So here it is. And
one question about the thread. What are those numbers to the left?
so these are addresses in the heap. So that little endian bitmap starts off at 0 and grows up to 50 meg in this case. Remember how it's in one of these inspectors.
I remember that yesterday you took those others and doing something with that.
Right. So I can. So for example, let me say, we're in the simulator. I can say self long at, and let's have long at this guy. And if I print that, lo and behold, it's 7F8. It is the saved. Right. So these addresses are, they're not indexes into the little endian bitmap because it's a Smalltalk object, and little endian bitmap has 32 bits. Right. So this has to be divided by 4 and add 1 to turn it into an index. Right. So if you look at look at the various implementers of long at, right? Here's the implementation in the VM simulator.
Yeah, I see.
Right.
So it's like an address in memory.
Right.
In some kind of
Right. And it is, and it's just that this address space goes from 0 to n rather than from a more interesting value in a typical C program. And in fact, I do keep the first. So let's do 0 to 2 raised to 32. Detect. So what's the first non-zero? Is 1024. So the first 1024 bytes are left 0, and it's a guard page, right?
These memory addresses are random, right? Like if you did that 10 times.
No, they're not random. They're exactly the same. It's one of the beauties that what happens is when I load an image, and the header of the image tells me how many objects and how much code space, right? And then I always allocate a byte array whose lowest address is always 0, and I'm always leaving 1024 bytes of zeros and then starting off. So this is absolutely repeatable.
It's abstract above the RAM, right? Like I'm just trying to differentiate between like the actual memory and then you created a space that's always going to have the same address.
Yeah.
Like it confuses me with where the pointers are moving in RAM and the address.
So what's actually happening in the object memory, I could care less. The garbage collector could move that heap, right? And so it's one of the reasons why I use the box simulator, and one of the reasons why I'm curious Igor, how you can manage to execute code directly out of the heap because it's not position independent. And if the garbage collector is moving things, surely it blows up. Maybe you're getting away with it because it's just so big that the garbage collector runs and puts it down there and then nothing moves. But it seems to me that you're being very lucky being able to do that. So, which is cool. So basically, these addresses are as they are because what I'm doing is loading an image and having the default size of machine code, which is a megabyte. And then I'm allocating a stack zone above that. So every time I run it, it'll come out with exactly the same addresses. And that's great for debugging. One of the things that's tedious, though, is that there are things that you do like, okay, let's add code that will trace each message send. And that actually adds some machine code to the start of a method. So in that case, if you switch on tracing, all of your addresses change, right? All of your machine code method addresses change. But on the whole, providing you keep most things constant, you're going to have exactly the same addresses in exactly the same sequence. There are strange variabilities like the clock, right? So that there's no facility for saying I want to start the system as if the clock was, 1 BC. Instead, it always starts off at the current time, and so that can cause variability, and I think that that's a pain actually sometimes. But on the whole, it's pretty repeatable, and I do use that a lot to make sense of it. So okay, when we go into the interpreter, the first thing we have to do, and I am repeating myself, is establish this exception handler. And then right down the bottom here is enter the interpreter. So when you enter the interpreter, the system isn't fully initialized yet. So stack limit. That's right, it's been set up. So the first time you go into the interpreter, yeah, that's right, it's down here on the stack. I think. Is it? No, I'm confused and I'm too tired to explain this. Never mind. Yeah, the first time you go, maybe it's only in the stack interpreter. The first time you'd enter into this, you'd initialize the stack pages. No, okay, this is the right. Okay. The real VM, when it's running in C, starts off slightly differently to the simulator. So that's what's going on here. So this is the inner loop of the simulated the simulated interpreter. So this is not the implementation of the interpreter that's in the production VM. So here's the implementation of the interpreter that's in the production VM. And it's very, very similar. It just goes right, true while true dispatch bytecode. But this one has some asserts in it. So it's going to assert that at each stage we've got valid instruction pointers, and it's going to run a block that we can use for setting breakpoints and stuff like that. And you could extend this with whatever you wanted to. And then the other thing is that we've got a bytecode count. And so every time it executes a bytecode, it increases a count, so you can stop at a particular bytecode, and things are very, very repeatable. So if you find that you have a bug after 1024 bytecodes, run the thing with 1023, right, as your breakpoint, and then step through that break, that kind of stuff. But what I wanted to do was get onto to cogeneration.
You have to be really lucky to have 1,000 bytecodes.
Yeah. Usually it's many millions. Yes, that's right. And you have to go for a T, and then come back. Yeah. But see, well, no. I mean, when you start implementing, you have bytecode, you have errors very early on. Yeah. But yes, as the thing gets more and more mature, those things get further and further away. So. So let me put a breakpoint on common send, and then just let the system proceed. So given that, oh no, it's the wrong one, isn't it? There we go. Okay, finally. So given that what I want to do is avoid compiling methods to machine code unless they're used more than once, the really easy way to do that, I think, is to say that if you find the method in the method lookup cache, you should JIT it. Otherwise, if you look it up, you should interpret it, right? Because if you don't find it in the method lookup cache, chances are this is the first time you're executing it. You may have overwritten a previous cache entry, but never mind. So okay, here's little digressions. One thing that I'm really irritated by with this VM is that the way that the simulator works is that you're kind of encouraged to put methods into the simulator that override and put in logs. Whereas there's another facility which you can use to put in code, which is kind of slang specific, and that's not necessarily so great in itself. It's got problems, but what you do with self-C code in Smalltalk is that you can include some code defining in a string what the slang should generate for C, and then what you want to do to generate what you want to do equivalent to that in the simulator. So I want to try and find some right. So here's some stuff in the threaded VM, which is saying, okay, let's just remember some state, and so this is the version that would be translated to C and executed in C, and here's the version that would be executed in the simulator. So if you want to, and you can you have to use those facilities sometime to get round the fact that you can't always simulate everything. So here's code that is saving a jump buff. So in Smalltalk, in the simulator, I don't have a jump buff. I have to use an exception. So in the simulator, I'm using an exception and throwing exceptions to simulate set jump long jump. And in C, I'm using set jump long jump and a long jump buffer. So if you want to put stuff in which is executed only in the simulator, you can use this self-C code empty in Smalltalk facilities. So this would have been much nicer written if in Common Send we used C code in Smalltalk and got rid of the simulator method, and then we had everything there. And then the other thing that you can do is when you're implementing code, is if you want to implement some helper method, that you don't, you know, some simulator method. So here's, for example, something that allows me to set the JIT in use by the interpreter, which I need obviously when I'm initializing the JIT, but I don't need in C because the whole thing is basically flattened. Is that you can include various helper methods. So there may be methods that you don't use in C or that are really useful that don't map to C. So for example, here's the method that I was using the other day to enumerate over all of the machine code that I generated. Methods do, and it applies a block to each of the methods. Well, that doesn't translate to C, right? There's no blocks in C. There's no way I can do this. So this is like scripting only. So if I was to try and translate that to C, it would fall over. So you use the do not generate pragma to say to slang, don't generate that code. And so the way that I think that the thing should happen is that the simulator should gradually shrink, and instead you use do not generate and C code in Smalltalk to add the simulation only code that you want, and then the system will get simpler. But anyway, so back to this. So basically, there's a hack here in the simulator that if you get a does not understand, it's going to give you a break. But here we are finally in the in internal find new method, and this is the thing that says, okay, if I find it in the lookup cache, I'm going to try and compile it to machine code. Otherwise, we'll just look up and edit and enter it into the class and continuing to interpret it.
Otherwise, do supersend.
Otherwise, do supersend.
No, I mean, otherwise, do the supersend. But in C, again, you don't have supersend.
Yeah, no, this doesn't do the supersend. What this does is if it's in the method lookup cache, it tries to compile it to machine code, but doesn't execute it. Otherwise, it looks it up and then enters it into the cache and then returns back to the interpreter.
No, what I mean that this method, if you look at stack interpreter, it will look at this part which is after if false.
Oh yeah, okay, yeah. No, I see what you're saying. So I modified slang so that you can do that. So I can show you some examples in the JIT, in the stack to register mapping JIT. So here you go. Here's what do you do to compile a Cog method with a sophisticated code generator. It has a variable that it needs to initialize, which is the number of method or block temporaries in the method. And then it, again, for checking, creates a little dictionary for making sure that the stack depth is right at all of the suspension points. And then it calls super. So in slang, there's code which says, if I see a supersend, look up the method, get the AST, and then expand it in place. Okay? And it probably doesn't work in every circumstance. And in particular, it's restricted where it's got to be a super of this method. You can't use a super arbitrary thing. But basically, you can use super. And it would have been nice, because I only added this recently, It would have been nice to have it in a few other places. So it's not used as much as it could be, but it is there. And super expansion node 4 is returned. This part, translation to C, is all of the slang machinery, and basically works by compiling a method, compiling each of the interpreter, each of the VM methods to a Smalltalk AST, and then Smalltalk AST has a VM maker extension, which then creates a T method and walks the AST and copies to produce nodes of this T-parse node hierarchy. And then those guys implement emit C code. Emit C code as various kind of things. So, you know, emit C code as argument, etc. So that's where the slang, the horrible Smalltalk to C translation happens. If you ever want to go look there. So let me put a breakpoint in here. And let this guy run. So let's see where we are. So, oh, I can't find anything. So we're in the middle of interpreted stream, write stream next put, and I might want to like open up the debugger and find out what the message selector is. Right. So here's the message selector, and then I could print an oop and find out that it's not on the heap. That's interesting. Oh, have we not? Really? Oh, no, that's right, sorry. Yes, that's a bug. So I want message selector in hex. One of the schizophrenic things is which base do you use, and so these guys take hex, and so it's is octet character that it's sending. If we have a look at right, so we're actually doing this send, an object is octet character, and that's right. Have I stepped up? Let me proceed and hit that breakpoint again. Okay, that's right. Oh no, hang on. There we go. So where are we now? Now I've hit my breakpoint in let's try and compile things to machine code. And we're in the heart of select, presumably early in system startup, where we're we're going over doing things with characters. What is it doing? Install key decode table. So there's something that happens early in startup. The interpreter has finally looked up a method and decided that it's going to JIT it, and it's grabbing some new method, and I want to start this anew. I'm not doing the right thing. Let me be honest here, and stop snowing you. So let's start up this thing again. And that's common send. I don't want, let me get rid of this breakpoint. And great, so now where are we? So finally we've hit the proper breakpoint, which is we're in the interpreter doing internal find new method, and we've decided that we do want to compile to machine code. So we are doing decompress from byte array, and that is a method which is actually used to install the current cursor. You have to decompress the cursor at startup. Kind of a weird way to find out how the system works from inside out. And you keep on looking at the thing that the system does, thinking, should it really waste its time doing this kind of stuff? There has to be a better way, but that way lies madness. The system is what the system is. So what is it doing? It's doing size, so it's done a send of size, and it needs to compile this to machine code if it's appropriate. So the first thing we have to do is the mapping from methods to their machine code is in the method header. Remember that the method header of a byte-coded method is always a small integer. So if the thing is odd, which this is, it's just a standard header, and then I hack it so that again using a similar trick to contexts, since the object header is only the header of a method is only accessed in very few places, I can use that header as a direct pointer to machine code. If I replace the header by the address of the machine code and get straight there, I can keep the real header in the machine code method, and so I've got this direct pointer from the byte-coded method to the machine code, and so header of. In the standard interpreter, it's just fetch the header index of a method, and header index is the 0th field. But in the co-interpreter, you grab the raw header, which is exactly what header is, and then ask, is it greater than the start of memory? Sorry, no, you don't do that. You ask, is it a non-integer object? So if it's not tagged, it's the address of the machine code method. So the first thing to do is if it's already compiled to machine code, we're not going to compile it again. But in this case, it's not. So then the next question is it too big? So standard policy in Cog for compiling anything is the number of literals smaller than a limit, and that limit by default is 60. But there's a command line parameter where you can change it, right? So this is just a standard simple way of getting rid of big methods. So right now, by default, any method that's got more than 60 literals, and $243 out of some 93,000, yeah, 93,000 methods. So quite small. Well, a third of a percent. So this really avoids wasting significant time, such as where's Unicode? Ah well, I can't find a good one, but you know, things like bothering to JIT huge. Well, never mind. So
and you don't check against the amount of bytecode, for example, or
no,
these are the only important.
no, I don't bother to do that.
I think one thing which can be done is in compiler to actually include some metrics.
Yeah, but then you're gonna the trouble with that is that you waste time attempting to compile.
No, in compiler, in Smalltalk compiler, you put in method header, okay, you can give me, or you can, and then in compiler itself you can say, okay, I apply this.
Right. Well, I didn't do that. What I did is in the VM there's a facility where you can say set the unused bit in the method header if the method is interpreted, and that's like VM parameter access to that. So what I did was run system startup, and then look at all of the methods which had been interpreted in system startup, and raise the limit until I didn't see anything interesting and performance critical on image startup being interpreted. So made sure that everything that was performance critical in startup was interpreted. And that's why I think I started off with 40 literals and I rose it to 60 literals. Right? So there's a facility in there where and there's an accessor in Smalltalk where you can ask it to clear. Well, you're right. So you can go through methods and clear all of those bits, but then you can ask the VM to mark methods that it interprets, and then you can find out what's the working set that's being interpreted. So I want to get onto this code generator. So the entry into the JIT is, have we looked up the method in the method lookup cache, and is it smaller than 60 literals? And if we get there, we will try and compile the guy to machine code. So at this point, we've gone from the interpreter to the JIT, and let's have a look at the Cogeneration Framework. So the CoGIT has a protocol called abstract instructions, and this is the assembler. It's very, very similar to Igor's native boost thing. So this is a very simple abstract machine. It's a 2-register machine, and there are, you know, jumps and moves and some arithmetic and stuff. And what those guys do is create an instance of an abstract instruction. You don't actually create an instance, sorry. When we remember what I said about wanting to stack allocate all of these objects in the JIT. The first thing we're going to do is make an estimate of how big the method is. So what I'm doing here is based on the number of bytecodes and whether the method has a primitive or not, I'm coming up with an estimate of the number of machine code instructions that I need to generate that method. And it's a conservative overestimate, but it's fine. So if you compile a method that doesn't have a primitive, then, you know, it leaves room for 10 instructions per bytecode. But if it has what am I talking about? That's nonsense. Yeah, that's right. 10 instructions per bytecode. But if the thing has a primitive, then what we're going to do at the start of it, after the checking code, we're going to compile a call on the primitive, or we're going to compile a primitive in line. If the JIT is smart enough, it can generate the machine code for a primitive and not have to call the primitive in the interpreter. So things like integer arithmetic, floating point arithmetic, all of the integer comparisons, those, and indeed block activation, those primitives the JIT implements by generating the machine code for. So if the method has a primitive, we allocate some extra opcodes. And so what's... Mm-hmm.
Do you determine the NPC of the method somehow?
Yes. So, okay.
Because then there is a trailer which can contain arbitrary bytes which you don't need to deal with.
So what's happening here is that we're just guessing and doing stack allocation. So we don't care if we over-allocate. And what we'll do is compile and find out how many we've actually used. So if we allocated some extra, we don't care, right? And then when we allocate the method, we'll only allocate as much machine code as we've actually generated. So at this stage, it doesn't matter if we over-allocate the number of abstract opcodes. An abstract opcode is not the same as the actual machine code. I'll show you abstract opcodes because we're getting into how the code generator works. I just wanted to get there slowly. Depending on the method, we make an estimate as to what the NPC is. You see here, I'm just saying that the NPC is the byte size of the method. But as I compile, I compute what the actual end method is, right? By figuring out what the latest continuation is, right? And we'll see that. So then, once I've got an estimate of the number of bytecodes, I'm going to add to the number of bytecodes this extra and multiply that by 10. And that's going to be the number of abstract opcodes I allocate. So now...
Sorry, I have a stupid question. In Cogit, there are all these methods that start with a capital.
Right.
Why is that?
So that's to make assembler stand out.
Why is that?
So...
You just identify those with a fragment?
Nope. No, I don't know. Where's my browser? So when I'm reading code, so for example, let me show you a method. Here's a method generates the machine code for calling a primitive which is implemented in the co-interpreter. And I find that by using capital letters here, the assembler that I'm trying to generate jumps out from me compared to the background stuff. So what it does is by using those capital letters, it makes the assembler readable. And it kind of just, it's so unexpected that I can read the assembler and ignore all of the noise. So I chose consciously to use capital letters only for the assembler, right? Because the assembler is you know, understanding the instructions that you're generating is really, really important.
The only reason is Eliot's perception.
Yep.
If I
Yep.
couldn't find compile Cog Method, I'm like, what is going on? I'm like, why is that guy capital? So,
Yep, that's right. And I think you can see it works. Doesn't it work even for you, that the assembler jumps out?
yeah, now they point it out.
And so it's really helped. And it's amazing how the eye is so good at filtering things. And one of the things that you'll see in my Smalltalk is that I'm a Becker. I believe in visual indented blocks because, you know, my visual perception is the only thing good about my perception. So I can't, you know, stuff that you know, people have the open square bracket here and the closed square bracket there. It's scary. I cannot deal with it. You know, everything has to be visual, and so you know, that's my style. That's the kind of Smalltalk that I can make sense of. So okay, what I've done here? Did I actually inspect that? Yeah. Let me explore it. So here I have. Oh yeah, I did. Here it is. There you are. Right. In the simulator, I actually allocate a proper array, and it's got these Cog IA32 compiler thingies in. And in the CVM, I've stack allocated space for those things using Allocate, and I've just zeroed the memory. Right. So in the simulator, we've got real structured objects. And in C, we've just got a big stack allocated array for the abstract opcodes. Okay, and let me show you the implementation. We had a look at that this morning, but we'll have a look at it again, of the allocate opcodes. So I was trying to illustrate use of allocate. So here's allocate opcodes, and in the simulator, here's the assignment to abstract opcodes. We want a C array accessor. What C array accessor is a wrapper that converts an array to zero relative indexing, because in C we use zero relative indexing. So if you put a C array accessor around an array, then the valid indices become 0 to n minus 1. So that's the way that you simulate the fact that in C you've got 0 relative indices. Right? So that's what's happening in the simulator, whereas in C, this is a macro, and it needs to be a macro because allocate, doing stack allocation, does not outlive its stack frame. So you can't call a method to stack allocate some space for you, because when it returns, that space is gone. Right? So you have to include it in line. So using allocate is a bit grotty. I didn't want to put that code in line in here, right? Because that would have been horrible. So the way that it works is this hack where it's a macro which expands in line, right? Hack, 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 hack. Never mind, it works. All right, so we ask for forgiveness. Hmm?
It's useful extension for Cogeneration. You can tell that this method actually should be in line as a macro.
Right, but yes, yeah, it would, and that kind of slang. But you know, slang is getting so creaky now that you know, I get nervous about trying to do stuff like that. But you're right. So okay, so now what we've got is we've got some abstract opcodes, and what does an abstract opcode look like? So an abstract opcode looks like. Let's have a look at its, well, it's like one of these. It's going to have an opcode, which is going to correspond to one of my assembly instructions. like this, and you see these guys have these opcodes in them, etc. And then it's going to have some number of operands. So here are the operands, and the opcode and the operands is enough to define the assembly instruction. So when I create an assembly instruction, I give it an opcode and I give it some number of operands, and right now we need up to 3 operands. But I'm not generating any machine code yet. And it's not until later on that when I've compiled all of the instructions that I can do things like start to work out how big a jump needs to be, if a jump needs to jump over some instructions. And I can start to size the machine code. And so what we'll see later on is that the first pass in and actually spitting out the machine code is to work out the maximum size of each instruction. And then once you've worked out the maximum size of each instruction, you can work out the maximum size of any jump. And then you can work out the sizes of jumps. And then you can actually spit out the machine code. And the way that the machine code is spit out is that you collect the machine code in each abstract instruction. So each abstract instruction has 12 bytes, I think, is what you need for x86, the longest 1, 2, 3, 4. 10 bytes is the longest instruction that it will generate. So the process that the JIT goes through is of compiling abstract instructions in this assembler. And then once it has a sequence of those abstract instructions, it sizes them, fixes up, determines their actual addresses in memory, and then computes their machine code, and then concatenates that machine code once it's allocated space for that machine code to go into.
This is so much more complicated than the 2.7 image and its interpreter that it must be a real testament to how slow that previous virtual machine is, because this is a really involved system you've got here, Eliot, and it's, I mean, in terms of conceptual complexity, this is like an order of magnitude more complicated.
At least.
2.7, yeah,
At least.
And just thinking about what you were saying about the price you pay for all these Smalltalk executions, that it's like the complexity here is a testament to how slow that previous system must be.
Yeah, but the complexity here. Look at V8. Look at a Java VM. Right, they all have this level of complexity. Look at a C compiler.
I'm completely ignorant, and I'm not making any comment. I'm just saying, from my personal perception, in 2 days, 3 days, that going from knowing nothing on Monday to here, this is my observation.
Yeah, I'm with you. But come on, I mean, I think people produce things that are conceptually much more complicated in Smalltalk. I would say that while this is far from simple, it's just mechanism.
It's pretty cool. I mean, I understand what you're doing, and I'm like, it's a pretty neat, we're going to put a little piece of assembly here, and it's informed, and it's not like you're going crazy with generating stuff. And from what I understand, there's not a lot. I like it, but I mean, there's a comment on how slow that stuff must have been.
Yeah. Yeah, and you know, the atoms out of which beautiful user interfaces are built are these incredibly simple operations like move register to register and add register to register, and you need hundreds of thousands or millions of them to do anything useful.
For this particular case, there is actually not much complexity. It's more typing than
Yes, exactly. It's a lot of methods, but it's actually kind of yeah, that's right. Yeah, that's a good point. Yeah. So okay, that's an interesting comment. So the first thing I need to do in order to be able to later generate code is to find out some basic things about the method. And one of the things that I want to do is find out how many blocks there are in it, because each block is embedded in the method. Each block is like a separate machine code entity, and I'm going to have to revisit the blocks and compile code for each of the blocks. So I've got to scan and count for blocks. Another thing I want to do is, if the method is sufficiently simple, I want to compile it frameless. I don't want to build one of these frames. I just want a little sequence of machine code. So if it returns an instance variable, if it assigns an instance variable, if it returns a constant, if it doesn't do anything complicated, if it doesn't include a send, I want to generate something that doesn't waste time building a frame and is quite simple. Another thing that I need to do is to relate branches between the machine code and the bytecode. So the input language to this JIT is a bytecoded method, and you know, if I inspect say if I inspect this, no, explore it. If I explore this method and look at its bytecode, the bytecode in this VM has jumps in it. So here's a jump false, here's a less than and a jump false down to bytecode 170, which jump to bytecode addresses. So if I'm generating machine code, when I see a forward branch, I don't actually know what instructions are going to be there. I know what the bytecode is, but I have no idea what machine code's there because I haven't got there yet. So forward branches are a real problem, right? Where are they supposed to go? So where they go is to a fix-up. So there's an array of labels, one for each bytecode, and what I need to do so that I can construct a forward branch is for each branch, where is it? Do I not do that yet? Does this not do that? Oh, hang on. Scan method, not scan. Sorry, that's right. I was looking at the wrong scanner. Sorry, that's right. So first of all, here's a fun thing. Igor knows only too well that at the end of methods there are arbitrary bytes which we can use for all sorts of things, because it was Igor who generalized the scheme so that we can actually put interesting metadata at the end of methods, like temporary names or whatever else we want. So the end of a method is not the last PC. So one of the things that the scanner does is maintain the latest continuation as it scans these bytecodes, and that starts off as the initial PC, and whenever you've got a forward branch, then that becomes the latest continuation, right? And whenever you find a return and the PC is greater than or equal to the latest continuation, you found the last possible point in the method, right? So the last possible point in the method is the first return that you find beyond the latest continuation. And the latest continuation is where you are or a jump forward. So one thing we do when we scan is come up with an accurate idea of where the end of the method is. I need to show you what these descriptors are, which I'll do first, but let me continue without showing you the descriptors. I'm kind of doing this all in the wrong order, but never mind. So for each bytecode, we've got a descriptor which has various pieces of information about that bytecode, and we're asking, for example, if we still don't think we need a frame, does this bytecode think that we do need a frame? And if so, you know, we're going to need a frame. And then here's the branch stuff. And so what the branch does is say, okay, let's decode the branch and find the target bytecode, and let's no, that's right. I'm wrong. Forward branches are easy. Forward branches, I can create a fix-up. That's right. That's right. Forward branches are a problem. When I come to compile a forward branch, in my fix-up, sorry, let me back up. So the way that you deal with the fact that branches are in the bytecode and branch to bytecode addresses is that there's an array of fix-ups. And what fix-ups are is just an indirection. Fix-ups are an indirection from a bytecode address to an eventually a machine code instruction. So they're just an indirection, and what they'll do is be places where I can link a machine code instruction to and say this machine code instruction is going to jump to that fix-up. And then that fix-up is going to later be associated with the real machine code instruction that's going to correspond to the bytecode that fix-up is standing in for. So when there's a forward branch, as I'm compiling code, I can say, oh, okay, well, jumping forward to that bytecode, let's put a fix-up there. Backward branches, on the other hand, are no good, right? Backward branches, I'm somewhere in generating machine code, and I want to generate a backward branch. If I haven't planted a fix-up there first, right, I don't know where it was. So what we do is as we scan all backward branches, we make sure that we set set the flag, set the target instruction to non-zero. Basically, set a flag in that says this is a valid fix-up. So now, when I've scanned the method, I know the targets, the bytecode targets of all backward branches. I know whether I need a frame or not. I know what the NPC is, and I know the number of blocks that are in the method. And those 4 pieces of information are absolutely vital to go on for compiling the rest of the method. So that's what scan method does. And here it gets back the number of blocks, and there are none in this one. So then what I need is a data structure for each block. So in this case, there are none, but imagine there were blocks. What's a block start? What a block start is something that knows that it's at a particular bytecode, and that it's going to have to hold on to the header for a block. So block, when we're running in the VM, a block activation has to have some method header that the frame can refer to, that's going to contain information from which we can find out what the actual method object is. So block starts are the things that the JIT uses to both manage creating blocks and eventually filling in the machine code for a block header. This will become clearer when I give you an example. That's a mess. Okay, so once we've done that initialization, we're ready to compile the entire method. So think back to when we looked at the inline caching behavior. What does a method look like? The first thing that we saw in a method was the abort call, which is the place that we can jump to when we get a send miss. We have to go and do that. And then the next, that's the prologue. Then the next thing is the entry checking code, which is fetch the class of the receiver and compare it against the register that we loaded at the send site. And if that's okay, we can continue. And then, if the method has a primitive, that's that's what we should do next. The first thing we should do is
Have you thought about reusing the class of receiver? Because when you do message send, you during lookup you are already fetching it.
No, when we're in machine code, we don't do lookups. When we're in machine code, all we do is these sends, right? All we do in machine code is we do a call, right? And we've loaded the register with some value, right? We just load the register with some constant.
Only if you machine code not interlinked with.
Right, and it's not. I mean, when this thing is running properly, it's spending almost no time in the interpreter, right? It heats up very quickly, and what it's doing is it spends all of its time in machine code, and that's one of the reasons why it's way faster. And when you're in machine code, you're not doing lookups. All you're doing is you're calling, right, 90% of your sends are these monomorphic things where you call some entry code, that extracts the class of the receiver, compares it against the value that you loaded, and you continue, right? So that's all it's doing. So there isn't any class to reuse. Right? So so once you've done the checking code, you can compile a primitive, which maybe, if it's simple enough, your implementer is intelligent enough to implement the machine code for. And if it's too complicated, you're going to have to do one of these system calls, kind of calls, and call the value in the interpreter. And then once we've done that, we can build a frame, because now the primitive has either succeeded or failed, and we're going to build a proper frame, unless it's a frameless method. And then we can compile the method body, which will implement the machine code for the method body. And then if there are any blocks, we can compile each of the block bodies so that that's the code for each of the blocks. And finally, at the end of the method, generate some code to dispatch to the block. So the way that we do block dispatch is basically there's a binary tree comparing a closure start PC and jumping to the relevant machine code. And that's why block dispatch in Cog is faster than in VisualWorks, because VisualWorks does a hash lookup to map bytecode PCs to blocks, no, to map bytecode methods to blocks. So I want to give you an idea. Today I want to give you an idea of of what the assembler looks like, and then the pushing the machine code out. I don't want to go into the JIT yet. So that the first thing that we've got in one of these methods is this standard 2 instruction sequence of doing a call of the abort routine after we maybe zero a register. So a compilation is just this process of initializing these abstract instructions. So now when I have a look at this guy, it's got an opcode in it. And this guy's got an opcode in it. So I've just compiled 2 instructions. If I have a look at the third one's still empty, right? Still nil. So that's what compilation is. That's what the assembler is. You just call issue this assembler instruction. What that does is initialize one of these abstract instructions. So what do the abstract instructions look like? So there's a pool dictionary, Cog RTL opcodes, whose class variables are all of the opcodes that we have in our abstract machine. And on the class side is the initialize method that defines all of these opcodes. And there's a comment in it which defines the semantics for the assembler. So capital R stands for a general purpose register, RD stands for a double precision floating point, CQ stands for a constant which can be squeezed into a small amount of space. CW stands for a constant which can hold an object pointer, which the garbage collector may move. So if you've got an object reference in machine code, you cannot encode that compactly because the garbage collector may come along later and move it. And so you've got to use the maximal space so that all of the possible values that the object can take on when the garbage collector moves it are valid. But that means that, you know, you would waste 4 bytes encoding all sorts of small constants, which you don't want to do. So what you do is introduce this split. So if you know that you're generating a constant which the garbage collector can't move, you can use CQ. So you'll find that there are and CQ and CW and move CQ R and move CW R. So the difference between those two is that you have to use CW for anything the garbage collector might move, and CQ you can use for everything else, so that you can generate more compact code. So then we may need some constants of a particular size where they're not the word size, but they have to be 64 bits or they have to be 32 bits. And then we've got some operands where we're talking about a word in memory, and what's in the instruction is the address of that word. And then we've got a byte in memory, and there's the address of that word. And then we've got you know, a memory word which is at the address of a register, and we've got a memory byte which is at the address of a register, and so on. So these define the suffixes that I can have on these opcodes, and then the opcodes come. And so here are the opcode names. So the first thing I've got is a label, and the next thing I've got is something that will align me on an 8-byte boundary, and things which just do fills and a no-op. And then finally I've got some interesting instructions. So the control transfer instructions are I can call, and I can return, and I can jump to the address in a register. And then I've got all of the jumps, and I have long jumps and short jumps, and so these are just standard you know, condition codes. So jump on equal, jump on not equal, etc., jump on less than or equal to, etc. And then we've got exactly the same, but for floating point. So for doing the floating point primitives and those comparisons. And then we've got data movement. So move a register to a register. Move a word at an absolute address into a register. Right? Move a register to an absolute word, etc. So you just go over the permutations. And this abstract instruction set is trivial to map down onto a whole series of processors, because I'm not doing anything SISKY here. So there's very few complicated instructions, right? So you see in the JIT there were all of these things where if you wanted to fetch a temporary variable and push it onto the stack, you didn't say push the value at an offset to the frame pointer. Instead, you said move the value at an offset to the frame pointer in a register, push the register, right? So by keeping this kind of SISKY, by keeping this kind of risky, it's going to be easier to map to things like ARM and stuff. Right? It does mean that the code quality is slightly worse, but basically this is an abstract machine that can be mapped to conventional 32-bit processors really easily. And it's Peter Deutsch's cunning thing in VisualWorks that I stole. So then, you know, we've got some shifts and some comparisons. And then here's something fun. When I define a new opcode, I need to assign it a unique number, and I need to declare it. So here's a horrible piece of introspection. that basically goes through that array and makes sure that all of those names are declared as class variables, and anything that isn't in that array is moved to undeclared. So it's a lovely piece of vile hack here, which basically takes this array of names and turns these into class variables with unique indices. So that populates this class pool. And so, you know, this one has its value, and this one has its value, etc. So it's just some introspective code that doles out those numbers. So then that's your machine model, and then there's a really simple register model. And the simple register model is there are 6 general purpose registers which we give generic names, and we will just try and use them. And yes, indeed, they are determined by the x86. And if we were on a RISC machine with richer registers, we'd have much more difficulty using those registers. So we've got a frame pointer register and a stack pointer register, which are the machine registers, but then we declare some register must hold the receiver or the result in a send. And we need a temporary register, and then we've got the class register, which is the thing that we use to load with the class tag at the send site. And then we may have another register which for sends which have greater than 2 arguments is the register that we're going to put the actual argument count in to pass to the runtime. And then we're going to have 2 registers that can hold arguments. And this is all shamelessly stolen from the HPS code generator that Peter took this approach, and it's very simple and it's really nice. And then we've got 8 floating point registers. And then it's up to the processor to map those abstract register names into actual concrete registers. So now we've got an abstract assembler for a two register machine, and we've got some registers. So that's your alphabet. Now the next thing you need is to create instructions out of those. So Cog abstract instruction is the data. We've got an opcode. We need to know how much machine code we're going to generate for this opcode. We need some operands. It's going to be at a particular address in memory when we emit it, and so on. But that is not the be-all and end-all. It's an abstract superclass. So the idea is that here's the compiler that maps that abstract RTL into x86 machine code, and it should have a sibling Cog ARM compiler which maps those abstract instructions into ARM machine code, and the same for PowerPC, etc.
Would you just do another sibling for 64?
And another sibling for x86-64, indeed. So here is the realization for x86. And so, for example, the code generator is as simple as here's a switch, a case statement over all of the abstract opcodes. So if you're doing and CQR, right, the maximum size is going to be 3 bytes if the constant fits in a byte. Otherwise, it's going to be 5 bytes if the register in which we're moving is EAX. Otherwise, it's going to be 6 bytes, right? So there's really simple concrete backend of an assembler here, which is working out how many bytes of machine code we need for each instruction. And then you notice that up here for the jumps, I'm doing resolve jump target. So this is the case where when the jump was created, the jump is jumping to one of these fix-ups. And at this point in the code generation pointer, we can follow the fix-up because when we got to the fix-up, we will have said, this fix-up corresponds to that machine instruction. And so at this stage in code generation, we can follow that indirection and get to the actual instruction that we generated for a particular bytecode sequence. It's like the first machine code instruction for a bytecode. So one part of the real low-level thing is just working out the maximum sizes of x86 machine code for all of this, and then the next one is is it gen concretize? Dispatch concretize. Here's the one that actually generates the machine code. So again, here's just a straightforward switch. And for example, let's look at concretize conditional jump. So to spit out the machine code for a jump instruction. Now let's have a look at something similar. It's simple. Let's have a look at say concretize or RR. That's good. And we can come back to that in some future insanity. Or there we go. Right. Okay. So to spit out ORing a register against itself, we need to map from the abstract register, which is the abstract register name, to a concrete register. So that's really simple. So temp_reg is going to map to EAX, and class_reg is going to map to ECX, because that's a useful mnemonic, and then EDX for the receiver, etc. And so these guys are, defined by some insane madness. Why the x86 is numbers things like this, I don't know. EBX is number 3, not number 2, but that's not number 1. That's the way they did it. I've never understood that. It's very, very weird. Gets you all the time. So now you've got the 2 registers, and on x86 OR is a particular opcode B, and then we need to encode a mod RM byte, which is a standard x86 thing for encoding registers and indexing and stuff. And then so we store that in the machine code array in the abstract instruction, and say that the actual machine code size is that. So once I've done that, I have just a big array of these abstract opcodes that are filled in, and we know the sizes of all of them, and then we can say to the allocator, give me this much memory, and just copy all of the machine code in place. So I want to, at this point, stop. It's 6 o'clock. It's late, right? And we can come back to this tomorrow at this state. It's a huge sigh. So we'll come back to this tomorrow and start off where we left off. Is this getting boring and too detailed, and you'd rather have other stuff, or it's going to be worthwhile pushing this through?
Push it through.
All right.
They're not going to have an opinion. They're afraid of you.
Haha! Excellent.
Maybe you will find some bugs.
Yeah, I think I've definitely found that's a cool bug with callbacks. Anyway.
So how many days did that save?
Yeah, lots. I've got to find out whether it is actually the bug yet.